So as usual, module 6, let's start with the learning objectives, right? Adders and multipliers. So this forms the heart of your ALU. So whatever we did till now is is a build up in order to apply those concepts and optimize this particular module. The ALU that we build in a microprocessor has all its components coming from these concepts, adders and multipliers in general, right? If you want to do convolution, then you have to do multiply accumulate, right? You want to do any other operation, this multiply accumulate is a very common thing. So typically the addition, and that is the accumulation, and the multiplication are operations that have been studied very extensively in the literature. Various architectures have been invented in order to reduce the delay. Every picosecond that you gain from optimizing the multiply accumulate operation or the accumulator in general will give you significant savings in the performance of the microprocessor, right? So therefore you will find various architectures that squeeze every single picosecond out of this operation, and that's what we are going to study in this particular module. What are the learning objectives, right? So first is you have to be able to design a full adder with the least PMOS stack size using self-duality principle. This we already saw a glimpse of in the earlier thing where I showed you the mirroring circuit, right? So this is something we have to be able to do. Construct adder architectures to reduce the delay from O of n to O of root n to O of log n, right? O of log n is going to be achievable only through something known as the carry lookup adder, which I am not going to cover here. It's a self-study part and you will have to implement it in the project. So please go look at it, study it on your own and implement that circuit and show it in your project, right? Then you should be able to draw timing diagrams to show signal propagation of various adders, right? What a timing diagram in the sense you have to show the arrival times at various points in the circuit and how and the optimization of the architecture is going to happen in order to sort of save or not waste the arrival times that you see there, okay? Then you should be able to design an array multiplier for both signed and unsigned multiplication. So we'll also look at unsigned multiplication where the numbers will be represented in 2's complement form, right? So we look at the math behind the 2's complement multiplication. Then we'll see how an unsigned multiplier can be converted to a signed multiplier with very minimal modifications and the math behind it so that it's, it is consistent, right? Then you should be able to optimize the array multiplier using the inverting property of a full adder, right? I'll deal with this today. Booth encoding, again, I really don't know if I'll have time, okay? If I'm running out of time, I may not cover it this time, but it's not too complicated for you to go and figure it out on your own as well, okay? Then design and implement a multiplier based on Booth encoding algorithm. So last two things, depending on time, I'll see if I can cover it or not, okay? So, okay, great. So let's start with the concept of an adder, and I want to look at a full adder directly. So a full adder is a block that takes 3 inputs, A, B, full adder, right? And it takes a carry in and gives out a carry out. And of course, it also gives you a sum. Okay? So let's put down the truth table of these signals. Sum, carry out. 0, 0, 1, 0, 1, 0. Okay. So what is the sum? It's essentially just A XOR B XOR C, right? So this is basically 0, 1, 1, 0. So if there are even number of ones, you get 0, right? And if it's odd number of ones, you get 1. 1, 0, 0, 1. What about carry out? 0. Essentially the carry out is you're adding the two numbers. If you have 1 and 1, right? If you have more than 2 ones, or if you have 2 or more ones, then your carry out, you have to take it to the next bit, right? That's like just like you do in decimal numbers. Only if the number goes beyond 9, you do it there. Here you do it if the number goes beyond 1. So therefore this will be 0, 0, 0. There are 2 ones here. You get 1. Again 0, 1, 1 and 1. Okay. There are certain other intermediate signals that are also very useful, and we will look at them. Okay. So let us look at what happens to the carry in, okay, in certain cases. So let us say that my carry in is 0 or 1, but my inputs are 0, 0. What happens to the carry out in that case? 0, 0, right? It means that irrespective of the input carry, the output is just killing the carry, right? The carry is just gone because the inputs are basically 0, 0. So this is what we are going to call kill, okay, K. Now what happens if the input, any one of them, A or B, happens to be 1, right? That is basically if you see these cases. Okay, this is, let me put this here, sorry, in black, it is kill, right? Or delete. Delete. Okay, so I will call this D. So what happens in the case of the blue arrows, where any one bit A or B happens to be 1, what happens to the carry out? Carry out equal to carry in, right? This is nothing but, let me write this here again slightly differently. This is 0, 0. This is C in, right? Therefore, this is nothing but propagate. The carry is simply being propagated from input to output. Okay. What about the last two cases? If both A and B happen to be 1, irrespective of what the carry in is, carry out is being generated. It means those two bits are simply going to generate a carry irrespective of what the input carry is. So therefore this is called generate, right? This is basically 1, 1. So therefore I can now define some intermediate signals: delete, propagate and generate. What is the logic function for delete? A bar, A bar, B bar. What is propagate? A XOR B. Any one bit happens to be 1, it goes. Okay. A XOR B. What is generate? AB. Okay. Key thing to note is none of these signals are functions of C in. Okay, so we'll see why we are even looking at that case. Why is A and B being treated differently from carry in? For that, we have to look at what we want to do in practice. In practice, we want to take this full adder and use it so that we can compute the addition of n bits at a time. So A and B are now going to be n bit vectors. A is some A of 0 to n minus 1 and B is B of 0 to n minus 1. I want to now get the sum equal to A plus B. This is not the logical OR, This is the summation, right? I want to create the sum of this and get the carry out also, because if there's an overflow, then I need to set that bit as well. So what do? You take this full adder that we created and cascade them one after the other. Right? So this is my A0, B0, A1, B1, A2, B2, A n minus 1, B n minus 1. Right? And this is going to be my carry in, and for you can assume that it's a separate bit or it's grounded, doesn't matter. The resultant out of these full adders will be S0, S1, S2 all the way to Sn minus 1, and the carry out will form the bit Sn. Right? If you add two n-bit numbers, you can get an n plus 1 bit answer. Right? So this will form Sn plus 1. Sn. I'm sorry, Sn. Yeah. N plus 1 bit. Right? This is the carry out. All these are full adders. All I'm doing is taking the carry out, right? Full adder, and cascading it like this. So now you look at what happens to the arrival times. This is something we did last class, right? This static timing analysis of propagating signals. Let's assume for now that the carry in, right, carry out generation takes 1 unit of time. Carry in generation time takes, some generation takes 2 units of time. Let's assume. Okay. So what happens, first of all, what's the arrival time of all the n bits, A and B? They are all 0. So the key thing is all the n bits arrive at the same time. They are all available at time 0. Right? Carry in also, let's assume it's available at 0. Okay. So at what point will S0 be ready? 2. What about the carry out of the first block? 1 unit. When will the carry out of the second block be ready? 3. Right? And what about the sum? 1 plus. So if this is 1, this will be 2, right? Yeah, 2. Correct. Now what about, so you keep doing this, you will find that my carry is being propagated from one stage to another stage, which means that the kth stage cannot finish its evaluation until that carry in has come, right? Which has to come all the way from somewhere. So this carry has to propagate from the 0th bit to the nth bit in order for the final result to be ready. So in some sense, while A and B are ready straight away, they are available at time 0 across all the n bits, right? So that's why what we are doing is this carry bit is more timing critical than the bits A and B in general. Okay. So now let's see what happens. Suppose A2, B2 happen to be 1. Right? A2 and B2 happen to be 1, 1. That's the carry out. Let's say, which is Sn, right? This one, Sn. Does it depend on Cn now? No. Why? Because that stage has generated a carry. So the generate signal, which is here in stage 2, which is A2, B2, you can just evaluate this even before that actual carry comes in. Right? So this is the reason we are trying to create these intermediate signals, just to make a decision on whether the carry, you need to wait for the carry or not. Okay? Here we are not making a decision, we are just evaluating it. Later you will see that I can make a decision based on this information. Okay. Similarly, the propagate here is A2 XOR B2, right? If that happens to be 1, that means the carry has to be propagated, which means that you have to wait for that carry to come. On the other hand, if G happens to be 1, then I can say that this from this stage onwards, everything can just evaluate with that generate signal. I don't have to wait for the carry in. This is the idea, the intuition behind creating these intermediate signals: generate, propagate, and delete. Of course, if A and Bn happen to be 0, 0, what happens to the Sn? Obviously, it's 0. It has simply killed the carry. It doesn't have to wait for Cin to propagate all the way, right? So first thing is, what is the critical path delay of this circuit? What is the critical path delay of this circuit? So is it Sn or is it Sn minus 1? Yeah. So you see what's happening, right? There is arrival time 0, 0, S0 is available at time 2, carry out is available at time 1. So that sum takes one more unit. Okay. But the idea is, while S1 is being generated, you propagate the second carry out into the next stage. That's why it is important to generate the carry before the sum. So we said that assume the carry out generation time is 1 unit and the sum generation is 2 units. Why did I make this discrepancy there? It's because the sum can take extra time to generate, but the carry has to propagate. So while this carry is propagating from this stage, this sum is being evaluated in parallel. You understand? So that carry has gone to the next stage, that evaluation is happening. While that is happening, this sum is already evaluated. So it's okay to delay the sum a little bit, but propagate the carry as soon as possible. Because that is what the sum is not going to hold up the next stage's evaluation. The carry will. Right? So I'm saying it's sort of a deadlock argument. Unless I tell you why I gave you this 1 and 2, you cannot argue this critical path correctly. So I'm just trying to resolve that deadlock. The carry is more important than the sum because that is propagating, sum is not propagating, and therefore it's okay to delay the sum in general. Okay, so it is okay to delay sum generation. Okay, so the maximum arrival time is obviously going to be for this particular bit. Now what is it going to depend on? Which arrival time is that going to be dependent on? You have an minus 1, bn minus 1 and the carry in. Obviously this is going to be the max arrival time. Then this will be the max arrival time. So the critical path will basically be like this. Right? So if you look at the delay of a ripple ladder, right? It is going to wait till n minus 1 carries are propagated, right? And the last sum is evaluated. What I'm saying is Sn will get generated before Sn minus 1 because of the way we have designed the adder. Carry comes before the sum, right? So this is n minus 1 times t carry plus t sum. It is not n times t carry, is all I'm saying. Okay, so here you can now substitute for n equal to whatever value and carry equal to 1, sum equal to 2, you will find the arrival time. and you can check for yourself. You construct 8 bits and just see if the arrival time is correct or not. Okay, so now this tells us that when we are creating our circuit for the full adder, we have to prioritize the carry out circuit over the sum circuit. Okay, because ripple adder delay goes as n minus 1 times t carry plus only 1 t sum. Right? It is okay to delay sum generation, but optimize C out generation. That's the key conclusion that we come to after this quick analysis. Right?